Let's now briefly summarize what we saw in this lesson and take a step back and situate this understanding with respect to the wider view of things. So first of all, we brought many concepts together in this lesson. Concepts that we saw before: identifier, variable, environment, instruction, procedure value, kernel language, and new concepts related really to the execution, to the execution state and the sequencing. Semantic instruction and semantic stack, where we combine the environment with instructions, the memory, all the variables together, the execution state, which is the stack plus the memory, the execution, which is the sequence of states, and all of this together, which is the abstract machine. We gave semantic rules for all the kernel language instructions. Note how modular this kernel language is. You can add a new instruction, you just have to add one semantic rule, basically, without changing anything else. So the kernel language, in fact, it was designed to be modular, but you can add new instructions to it by adding semantic rules. So we gave the semantic rules. We also proved program correctness. We showed how you can use the semantics to make a bridge between the specification, so what you want, and what the program is actually doing. So semantics is the way to bridge this gap. So another point is discrete mathematics. So the abstract machine is built with discrete mathematics as opposed to continuous mathematics. And in fact, for our students at UCL, here in Louvain-la-Neuve in Belgium, it's the first time that they see a complicated system built with discrete mathematics. And even our engineering students, who are proud to be very good in mathematics, they're used to integrals, differential equations, complex analysis, piece of cake for them. All of this is continuous mathematics. They have not seen a complicated system built with discrete mathematics before they take this course. Discrete mathematics is very important. That's how computing systems work. They are discrete, both the software and the hardware. And if you understand that, surprising behavior and bugs become less surprising if you understand the kinds of problems that can occur in such systems built with discrete mathematics. And unfortunately, too often, continuous models are used for computing systems. You take averages, for example, where you try to predict things. Sometimes that works, but only within certain boundaries. Outside of these boundaries, the inherent discreteness of computing systems shows up. And what's more, all of these lessons also apply to the real world. So the real world, you can describe much of it using continuous mathematics, but you also need discrete mathematics. So why is semantics important for the programmer? Well, now maybe after this lesson, you have a clearer view of this. In fact, as a programmer, you are extending the semantics. You are building new semantics. You're writing specifications, you're designing and implementing abstractions, which is things we're going to see very soon. You are extending the system, reasoning about your system. So you are taking the system semantics and extending it with your own semantics. And this leads to the following point. Any complicated system that you design, a system that has parts that interact in interesting ways and that might be unpredictable, programming languages and programs are examples of that, this should be done hand in hand with a semantics. Don't just design the semantics at the same time. And the only way to avoid unpleasant surprises and guarantee a simple mental model for the programmer and the user is to have a simple semantics. And this is a very strong thing. If you have a simple semantics, even if you don't understand it, or even if you don't even know it exists, if there exists a simple semantics of your system, you will reap the benefits. So users of your system will reap the benefits of the fact that internally it has a simple semantics. things will just work. They will just feel right. Even if they can't exactly say why, things will be consistent if you do that. And then a final point, what I like to say is that semantics is in fact the ultimate programming language. Thinking at the level of semantics, writing pseudocode or pseudo semantic rules or pseudo semantics is really what programming should be. It's the highest level of programming. So for me, semantics is the ultimate programming language. One example is that we've seen already, invariants are the ultimate loop construct. You don't want to write explicit loops where variables are assigned or things are executing repeatedly. No, you want to think in terms of invariants. And what we will see, data abstractions are extensions of the system, are essentially new kernel language instructions. So you are building new system when you build data abstractions. And data abstractions as new kernel language instructions is inherently a semantic thing. So to finish this little summary of this lesson, semantics has many, many, many uses. So let me just briefly go over them. For design, like we saw, making the design simple, predictable. For understanding, especially the nooks and crannies. That's exactly why you need semantics. For verification, anytime you use the word correctness, it means you need semantics. For debugging, a bug is only a bug if you know what a correct execution is, which leads to semantics. For visualization, any visual representation must be correct. For education, the semantics, because it shows the whole system, is pedagogically very useful. Finally, for program analysis, of course, and for compiler design, it's very important. And a final point, in order to understand program execution, we do not need to bring in details of the processor architecture or compiler in order to understand many things about programs. One thing that we did not treat in this lesson, but that you can see in the textbook, is garbage collection, the automatic memory management. This can be understood completely using our abstract machine operational semantics. This is explained in the textbook. And finally, for the rest of the course, we will pick and choose and use bits of semantics when we need them to help us go forward and understand new things.